In this lesson, we will learn how to create the design and procedure for your authentic science learning experience. Now that you have an exciting and engaging science question and a well-thought-out hypothesis about your answer, it's time to create a well-designed experiment to test it. In Support NGSS Scientific and Engineering Practice Number 3, Planning and Carrying Out Investigations. So what constitutes a well-designed experiment? It needs to be a fair test of your hypothesis. A fair test happens when you change one factor or variable in a system and keep all other conditions the same. For example, if we wanted to test how car design affects speed by racing two cars down a ramp, the only factor we should change is the design of the car. Giving one car and not the other a push would not be fair. Your test should always have only one variable that you change. This is known as the independent variable. In our example, the independent variable is the design of the car. What the independent variable is and how you change it is an important design decision in your experiment. In our example, we might want to change the wheels, weight, shape, and size of the car. But we should only change one of these at a time, or else we will create more than one independent variable. The goal of your experiment is to measure or observe what happens when you change your independent variable. To do this scientifically, you need to decide on one specific factor, the dependent variable, that you will study. In our example, the speed of the car is the dependent variable. We want to know what happens to it when we change the design of the car. Does it increase or decrease? How you measure or observe the dependent variable is another important design element of your experiment. In our example, we could keep it simple and just observe which car got past the finish line first. Or we could time the cars and even measure or calculate their velocity and acceleration. How you measure the dependent variable should be determined both by the rigor required to answer your question in a scientific manner and by your learning objectives. In our engineering class, the focus is on car design principles, so observing who wins is enough. But in our physics and math classes, we want our students to understand and apply speed equations, so we ask them to measure and calculate velocity and acceleration. In an ideal experimental system, the only things that change are the independent variable, and if there is a cause and effect relationship, the dependent variable. But real experiments are never ideal. There are always other factors that can change and possibly affect your results. In our example, how we release the cars will affect how fast they go, as will the length and incline of the ramp. To do a fair test, we need to control these factors, the controlled variables, to keep them as constant as we can during the experiment. In our case, we might want to build a release gate for the cars instead of relying on two students to let go. It is often tricky to identify the controlled variables in an experiment or keep them constant. For example, in this simple experiment, what would happen if the weather changed when you provide different feed, or if a crowd of people came by the feeder just before you counted? This is going to impact your results, but how do you control it? Perhaps you can use two feeders so that you can test both bird feeds at the same time and under identical conditions. How you control these other variables is yet another important design decision in your experiment. There are general strategies you can take to reduce or at least manage variability in your experiment. First, keep the experiment as simple as possible. Limit time, equipment, and resources. Every time you add something, you're adding a variable that may confound your results. Second, make sure that you measure and document the values of key controlled variables you have identified. For example, in our car experiment, we measure the incline of the cardboard ramp before and after the experiment. It sometimes sinks down when we use it. And note down other factors that you think might be important. For example, the weather or time of day and place where you performed the experiment. You may find that these have an impact on your results. Finally, practice. We are the greatest source of variability in most of our experiments, so build in the time and opportunity to do a test run, especially if there are tricky pieces of equipment or finicky manipulations involved. Once you have designed your experiment, you'll need to develop an experimental procedure that provides step-by-step instructions on how to run it. Your procedure needs to enable your students to run the experiment accurately, so that they test your hypothesis the way that you have designed. To accomplish this, you need to define the critical elements of the experiment clearly and give specific quantities including units where appropriate and how they should be measured. The procedure also needs to help your students determine if the results they obtain are consistent and meaningful. To do this, they need to obtain enough data to compare. We'll dig into this more in depth in our next lesson. But a general rule of thumb is to repeat an experiment 3 times, or have a sample size of at least 20. And finally, your protocol should help your students work autonomously. This gives you the opportunity to give them the personalized coaching they need to further their learning and growth, instead of having to spend your time repeating instructions, often many times over. Your procedure should provide sufficient detail so that your students can follow it step by step. But keep it as short and focused as possible. Avoid clutter and distractions. Don't make running the experiment more complicated than it needs to be. This is not the place to include background reading or any other materials that don't relate directly to the execution of the experiment. A good procedure will list the materials required and provide instructions on how to set up the experiment, and then run it. There are a number of simple design elements and tools that will make your protocol effective. You will want to include checkpoints along the way to make sure your students are on the right path. This could be a checklist of materials or steps in the experiment. With digital tools, you can track these checkpoints in real time. For example, by having your students use a shared Google form to document their progress, or you can use a customized student response tool like Socrative to see how they're doing. Also include visuals, either static images or video, that explain how to run the experiment, especially the tricky or potentially dangerous parts. These often include how to set up and use equipment and how to take measurements and make observations. And this brings us to data collection. This is such an important part of the experimental procedure that it's getting its own section. Without data, our authentic science learning experience becomes little more than an opportunity to play around with some fun science toys. And data is integral to many of the NGSS scientific and engineering practices. Yet the basic step of collecting data is often overlooked when we design our lessons. So make sure your experimental procedure explains what measurements and observations need to be taken. And be careful not to clutter your experiment with requests for information that is not being generated by the students, but can be obtained later through data analysis or research. For example, do ask your students to collect the pH of the solution they are using, but don't ask them its chemical formula. Do have them note how many light bulbs are on in a room, but don't ask them to determine how many kilowatts per hour the bulbs use. Do have them picture and describe the bird they see, but don't ask them to determine what type of bird it is. Make sure your experimental procedure tells your students when they need to collect data. In your design, remember that many of them are going to get distracted and lose focus. So try to break up data collection into short bursts around a single theme, topic, or activity. And finally, make sure your experimental procedure tells your students how they need to collect data. Promote good data collection habits by rewarding your students. And use digital tools to collect data. This makes it easier to store, review, use, and share later on. Many generic tools like Microsoft Excel and Google Sheets can be adapted for this, or explore custom-built data collection and sharing tools like ACERN's Discovery platform. You are now almost ready to switch from experiment to analysis. Just before you do, you should take a few minutes with your students to determine whether they've successfully completed the experiment and whether they struggled or still have work to complete. This will help you manage the next steps better and will help you improve your experiment next time around. Also, ask your students for their first impressions of the experimental results to get them thinking about their data in a structured, critical manner. And start tackling additional NGSS scientific and engineering practices. For example, ask, do you think your solution was an acid or a base, and why? Or, what do you think that bird was? And finally, seize the moment and have them share ideas and questions the experiment has inspired. These are likely to range from hilarious to inspiring, but will always be powerful and present good learning opportunities.